All right, now we're ready. Well, I know I rely on you guys to figure out where I am, but I figured it out before coming to class, and we're on question 23 in chapter 5. So that's where we are. Now all I have to do is find the right page. All right, I found it.
207?
Yeah, page 207. The City of New York Housing Authority vacancy survey showed a total of 59,000 units, and for rent stabilized and some other number for rent unstabilized. For the rental units, let's see, for these rental units, the probability distribution for the number of people living in the house are as it shows below. Okay, so I got that. Bunch of numbers. A, what is the expected value of the people living in each type of housing unit? Okay, so my expected value for the rent controlled. That's going to be a summation of the value times the function is what we're looking for. All right, so that'd be 1 times 0.61 plus 2 times 0.27 plus 3 times 0.07 plus 4.04 plus 5.01 plus 6 at 0. And getting out our calculator, we find that's going to be, I don't know what that's going to be. Oh, I'm on, good. $1.57. And continuing on with A, the expected value of the rent subsidized guys is going to be the same thing, summation of the number times the function, and 1 times 0.41, 2 times 0.3, 3 times 0.14, 4.11, 5.03, 6.01. And I'm putting that in my calculator. I see that that's probably going to be 2.08. The B question, what is the variance of the number of persons living in each housing unit? The variance. Okay. B. We want the summation of the difference between the mean and the value squared times the function. All right. So that's what we're going to do. And we want first rent controlled. So we're going to do the rent controlled guy first. And, okay, 1.57 minus 0.61 squared 0.61. No, 0.61? One, because I have one person in the house, plus 1.57 minus 2 times 0.27, that has to be squared, plus 1.57 times minus 3 squared 0.07 plus 1.57 minus 4 squared plus 1.57 minus 5 squared 0.01, 1.57 minus 6 squared 0.00, and we end up with some number, 0.75. And then we want the variance of the rent subsidized guys. And we're going to do it slightly different this time, but we're going to end up with the same number. So that's what we're doing. And it's 2.07, right? 2.08. Okay. 1 minus 2.08 squared 0.41. 2 minus 2 minus 2.08 squared 0.3. 3 minus 2.808 squared 0.4. 3 minus 2, well, we already did that, 4. 2.08 squared 0.11. 5 minus 2.08 squared 0.03. 6 minus 2.08 squared 0.01. Okay, and we're going to throw that in our calculator, and I'm going to end up with 1.41. Make some comparison between the number of people living in rent-controlled units and the number of people living in rent-stabilized. Okay, so that looks pretty simple. Rent-stabilized have more people. More people, P-E-O-P-L-E, than rent-controlled. So rent-stabilized means they were built they're newer. Rent-stabilized are newer, they're going to have more people in them. You want to live in a new house or an old house in New York City. Well, you don't want to live in New York City at all, that's beside the point, but probably want to live in a new one.
Can you scroll back a little bit?
Yeah.
Thank you.
Okay, 29 is next. In San Francisco, 30% of the workers take public transportation daily. A sample of 10 workers, what is the probability that 3 workers take it daily? A sample of 10 workers, what's the probability of less than 3 take it daily? Okay, so our probability function is the number of items taken some number at a time times the probability times how many times 1 minus that probability and minus that many. Okay, so we want 10 things taken 3 at a time. We want 0.3 raised to the third times 1 minus 0.3 raised to the 3 minus 10, 10 minus 3, 10 minus 3, 10 minus 3. That's an n for number. That's an n for number. That's the same n.
What do you do though with that first 10 and 3? Do you times it, minus it, or what do I do with it?
Okay, so that's going to be 10 factorial divided by 3 factorial times 10 minus 3 factorial times 0.3 cubed times 0.7 to the 7th. Okay, well, 3 factorial, 10 minus 3 factorial is 7 factorial, and 10 factorial divided by 7 factorial would be 10 times 9 times 8, and then that'd be divided by 3 times 2 times 1. 0.3 cubed, 0.7 to the 7th. 2 can go into there 5 times, 3 can go into there 3 times. Well, it looks like we're down to putting in our calculator. 5 times 3 times 8 times 0.3 raised to the third times 0.7 raised to the 7th. Well, calculator did it pretty quick. 0.267.
So you can just put that top part in your calculator and then do the answer.
Say again?
You can just put that part right there, the middle one.
This one?
No,
That one? Yeah, you could put that in your calculator, yeah. And I'm pretty sure this is, if I go 10 items taken 3 at a time, I get 120. Do I get 120 down here? 15 times 8? 15 times 8. Yeah. So, I could put in my calculator 10 items, my RC, my NCR key, if I have that on my calculator. NCR key, 3 at a time, times 0.3 raised cubed times 0.7 to the 7th. I could do that as well. So I don't necessarily have to go through the factorial thing if I remember that that notation is the combination of 10 items taken 3 at a time. And my calculator.
Can you repeat that one more time? I'm sorry.
If I can find my NCR key on my calculator, if I know where it is, then I can use it and calculate 10 items taken 3 at a time without going through the factorial notation. If I can't find that on my calculator, then I don't have any choice. I have to go through the factorial notation.
So you hit 10, second, 8, and then the number.
Alright, so that would be the probability,
And then the number like 3. And then enter.
so this is the probability of 3 people doing it. Now, for the B part, we want the probability of x being less than or equal to 3. Okay, so that's going to be 1 minus the probability of having 0 minus the probability of having 1 minus the probability of having 3. So that means we're going to have to calculate f of 0. F of 0.
Can you go back to that first page?
Okay, so the probability of being greater than 3 is 1, the probability of everything, minusing the probabilities of only having 0, 1, or 3 out of 10. So I have 10 people, 0 of them could have not taken mass transit. 1 of them could have not taken it, 3 of them could have not taken it. I subtract those probabilities away from 1, and that tells me with a probability of greater than or equal to 3 people taking it.
Would you also need f of 2?
Yeah, I need that's f of 2.
Oh, okay. Sorry.
Yeah, that's a good call. I ran out of room over there and I didn't go whatever the excuse. Yeah, that's f of 2. Alright, so I need f of 0. So I need the combination of 10 things taken 0 at a time times 0.3 0.3? Yeah, 0.3 raised to the 0, 1 minus 0.3 raised to the 10. The probability of one person doing it, 10, the combination of 1, 10 at a time, 0.3 raised to the first, 1 minus 0.3 raised to the ninth. Probability of 2, 10, combination 2, 0.3 squared, 1 minus 0.3 to the 8th. Okay, well this is going to be 1. Would it be 1? Yeah. Because this is 10 factorial divided by 0 factorial times 10 factorial. The definition of 0 factorial is that it's a 1, so that ends up to be 1. So 0.3 to the 0 is 1. So now all I need is just 0.7 to the raised to the 10. 0.7 raised to the 10th. 0.028. And 0.028. Ran out of room. We'll throw in another 2 just for the heck of it. And now we have 10 factorial divided by 1 factorial, 9 factorial, 0.3 raised to the first, 0.7 raised to the ninth. So this is going to be 10 times 0.3 times 0.7 raised to the ninth. 1, 2, 1, 1.
Oh,
1 minus 0.3.
yeah, okay.
Right? And the last guy, 10 factorial divided by 2 factorial, 8 factorial, 0.3 squared, 0.7 to the 8th. And I'm just going to go 10, combination of 10 things 2 at a time, which is 45. 45 times 0.3 squared times 0.7 raised to the 8th. 0.2335. Okay, so the probability of more than 3, 1 minus 0.0282 minus 0.1211 minus 0.2335. And now we're ready for a final answer, 0.6712.
Don't you also need that F of 3?
No,
You don't?
because it's 3 or greater. Greater than or
Oh,
equal to 3.
Oh, okay.
If it were not equal to 3, then the answer would be yes. I would need f of 3 also.
Okay. So it's equal, okay.
Yeah.
Greater or equal to.
Greater than or equal to 3. 35. Do you guys have the technology to email me your test? So we would also have the possibility of I could pass out the test, you could start it, and if you didn't get to the point where you wanted me to grade it, you could email it to me over the weekend. I could grade it and send it back for your second opinion. So that's a possibility too.
You can't do class grade yet.
Well, what I'm thinking is that we may not get done with chapter 6 tonight. I mean, it's half past the hour. We managed to make it through 2 problems already, and we're still in chapter 5. So that's what I'm thinking. Okay, back to what I was doing. Number 35. The Census Bureau population shows 28 percent of individuals ages. Oh, I'm sorry. A university found 20% of students withdrew without completing the introductory stats class. Assume that 20 students registered for the course. Okay, so 20% normally go, and I have 20 students still in total. Okay, so I want to find the probability that 2 or fewer withdrawal. So I want the probability that 2, the probability that 1, and the probability that 0. So I'm going to add those guys together. Okay, so I've got 20 students, taken 2 at a time, 0.3 squared, 0.2 squared, 0.2 squared, 1 minus 0.2 to what? To the 18th? Yep, that's what that's saying. Plus 20 students, 1 at a time, 0.2 to the first, that's going to be a 0.8, right, to the 19th, plus 20 students taken 0 at a time, 0.2 to the 0, 0.8 to the 20th. Okay, so that's the math I'm looking for. Okay, so I got 20 things taken 2 at a time, which is 190. 190 times 0.2 squared times 0.8 raised to the 18th. So I got 0.1369 plus 20 things taken 1 at a time, which is 20, times 0.2 times 0.8 raised to the 19th power. 0.0576. This is 1, that's 1. 0.8 raised to the 20th. 0.0115. So 0.0115 plus 0.0576 plus 0.1369. Boom. 0.206. All right. Good enough? Double dog dare you to do it without thinking that you're in the right chapter. Our mind has to be in the chapter we're in order to do the problems we're in. B. Compute the probability that exactly 4. Okay, so the probability of 4 withdrawing. Okay, 20 things, taken 4 at a time. Who put that line there? Point 2 raised to the 4th power. 0.8 raised to the 16th power. Okay, 20 things, taken 4 at a time, times 0.2 raised to the 4th power, times 0.8 raised to the 16th power, and I got 0.2182.
How many significant figures do you want us to go?
Oh, I don't care. The author's keeping 4 for some reason. I wouldn't go any further than that.
So if we put down 3, that would be okay.
That'd be, yeah, if you put down 3 there, that'd be
Even
awesome.
on a test?
Yeah, especially on a test. Yeah. C. Compute the probability that no more than 3. No more than 3. Probability. No more than 3. Well, that'd be the same as the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3, right? So all we have to do is calculate the probability of 3 and then add it to what we had in the A answer. 20 things taken 3 at a time, 0.2 cubed, 0.8 raised to the 17th. 23 times 0.2 cubed times 0.8 raised to the 17th. 0.2055054. So we take our A response and we add the probability that 3 goes into it, and we end up with what?
Is that a Y?
There's no Y anywhere. That's a 4. No, we can't do that. We got to go 1 minus the probability of 0, the probability of 1, the probability of 2, the probability of 3, 1 minus. Now we already know what that is because that's up here in A. So we come up to A, 0.026. 0.206. 0.2054, and they end up with point what? 5886. Okay. The D answer. Compute the expected number of withdrawals. D answer. So the expected number of withdrawals going to be mu, and that's going to be NP, 20 times 0.2. 4.
If you do that 1 minus 2.06 plus 2.204,
Mm-hmm.
you get 0.54. That's what I came up with.
Okay.
I don't know if that's good or
1 minus 0.206 minus 0.2054. Boom. Nope, I get that same number.
Oh, do you?
Yeah.
Maybe I was missing a decimal.
All right, next is 41.
I was just missing a decimal.
Yeah.
Sorry.
Number 41. During the period of time that a local university takes phone-in registrations, calls come in at the rate of 1 every 2 minutes. 1 every 2 minutes. A. What is the expected rate of calls per hour? Expected rate of calls per hour. Okay, so mu is going to be NP. Okay. The probability of getting a call. I would say 30 would be the answer I want, right? That would be my first guess. And so that has nothing to do with anything, and we'll just go with 30. Yeah, because I have 2. Let's say 2 per minute times 60 minutes per 1 hour. 120 per hour? No. It's 1 every 2 minutes. So 1 every 2 minutes, and then I divide 2 into there, and I get 30 every hour. Okay, so I can handle that one. B. What is the probability of 3 calls in 5 minutes? Okay, so I want the probability of 3 calls in 5 minutes. Oh, that's what I'm looking for. So I expect 1 call 5 every 2 minutes. In 5 minutes, my expected rate, mu, would be 5 minutes divided by 2 times 1. So I'd expect 5 calls, 2/5 of a call. 5 halves. 5 halves of a call is my expected value. Okay, that's not what we're looking for. We're looking for the probability of 3. Alright, so probability of 3. And this is a continuous thing. And if we look on page 220, we find that f of x is equal to the probability, the mean, to some power x. So that'd be 3 e to the minus 5 over 2 divided by 3 factorial. Okay, so that's what the equation on page 220 tells us to do. Now the issue is, can we put it in our calculator and have it do that? Okay, so I got 5 halves. Well, that's not going to work that way. Parentheses, 5 halves raised to the 3rd times, where is my exponent key? Exponent, e raised to the minus 5 over 2 divided by 3 factorial. Boom. I put it on my calculator and I get 0.214. So the probability of getting 3 calls in 5 minutes, 0.214. And next we want the probability of no calls in 5 minutes. Okay, so C, the probability of no calls in 5 minutes. All right, so that'd be 5 halves raised to the 0 e to the minus 5 halves divided by 0 factorial. Okay, well 0 factorial is 1 and 5 halves raised to the 0 is 1, so all we need is just e to the minus 5 halves. Okay, so e raised to the minus 5 halves. 0.0821. The probability of getting no calls in 5 minutes. All right, next problem, number 47.
What was that answer?
0.0821. Less than a 10% probability that I can sit there not doing anything for 5 minutes. And 47. Oh, right. Now we get the hypergeometric probability distribution. Oh, yeah. Just what we always needed. 47. Suppose capital N is 15. Little r is 4. What is the probability of x equal 3 for n equal 10? And luckily there's only one page between where we were and where we are, so the equation ought to be pretty close. Alright, so the probability of x is going to be r x n minus r little n minus x divided by capital N, little n. And all those are combination things. Okay, so all we got to do is just fill in the blanks. So the probability that x is going to happen. Little r, 4. So I have 4 things taken 3 at a time, times capital N, 15, minus 4 is 11, little n minus x is 7, divided by capital N, 15, little n, 4. Okay, so I'm going to put in my calculator 4 things taken 3 at a time times 11 things taken 7 at a time divided by 15 things taken 4 at a time, and my calculator says 0.967.
How'd you get 11?
I have no idea. Oh, 15 minus 4 is 11. So 15 minus 4 is 11. 10 minus 3 is 7.
That's right, sorry.
15 over 4. Unfortunately, little n is 10. So this 4 down here is really 10. Yeah, that's a bummer, I know. That's one of those n's and r's look the same thing. All right, do it all over again. 4 things taken 3 at a time times 11 things taken 7 at a time divided by 15 things taken 10 at a time equals 0.4396 or thereabouts. Much better. 53. Okay, 53. The Barron Big Money Poll asked 131 investors across the United States about their short-term investment outlook. Okay, so we got 53. We've got 131 investors, 4% bullish. 53. Very bullish, very bullish. 39% bullish. 29% neutral. 21% bearish. 7% very bearish. And now we have bulls and bears all looking the same. Alright, so 4-0 for writing the problem down. Now, it looks to me, in any survey, somebody had to not make up their mind, right? 39 plus 4 plus 29 plus 21 plus 7. 100%. So this particular survey, everybody knew an answer. That's strange. Let x be the random variable reflecting the level of optimism. Set x equal to 5 for bullish and 1 for very bearish. So this is going to be a 5, 4, 3, 2, 1. Develop a probability distribution for the level of optimism of the investment managers. Okay. So you got all that memorized? Okay, I'll move down some. And okay, so x, we've got a 1, 2, 3, 4, 5. We have a probability of that being that x, 0.07, 0.21, 0.29, 0.39, 0.04. Okay, we have x times the function of x, 0.07, 0.42. Oh, too late in the day. 0.87. 1.56. 0.2. Okay. We have a x minus mu. Okay. Now we're going to come down here and say the expected value is going to be this number, which is our mu. I'm going to add these guys together. 0.07 plus 0.42 plus 0.87 plus 1.556 plus 0.02. Boom. 2.94. Maybe not. I'll do it again. 0.07 plus 0.42 plus 0.87 plus 1.56 plus 0.2. Boom. There, that's better. 3.12. Okay, so now we're going to go with the value minus mu. 3.12. Alright, so I'm going to have minus 2.12 minus 1.12 minus 0.12 0.86 1.86. There. Then I'm going to look at x minus mu squared. Okay, so that's how I look at next. 0.212 squared, 4.49. 1.12 squared, 1.25. I'd probably have more significant digits there, but I'm running out of room. 0.014. 0.74, 3.45. And then, oh, I can move this over. Oh, I didn't know I could move that over. I got plenty of room. Then I want x minus mu squared times the function of x. And when I do the summation of that, I'm going to get the variance, is why I'm doing that. Okay, 0.31, 0.26, 0.0, 0.3, 0.4114. And I add those guys up and I get 1.03, which is my variance. Now, what was I supposed to do for the problem? Develop a probability distribution. Okay, I did that. Compute the expected value. I did that. Compute the variance and the standard deviation. So I still have to get the standard deviation, which is going to be the square root of 1.03. If I put it in my calculator right, 1.03, boom, 1.01. So the standard deviation. Comment on your results. Comment on my results. It's time to sell. Everybody's bullish, right?
Huh?
Most people are bullish, so it's time to sell. The market's up. The market's up and going up. Time to buy. Okay, I'll go with time to buy. Doesn't matter if you buy or sell, right?
Don't you want to sell when it's high and buy when it's low?
Yeah, but it's still going up.
Oh,
Yeah, time to buy for a little while. Well, you know, you could, one strategy is to buy low and sell high.
right.
Another strategy is just to buy. So Grandma Zosky got C stock, which is Citicorp, when her dad died in 1919. The family hasn't sold it yet. My mother still has it. So it was bought in 1980. She got it, the family got it before 1919. We've been getting dividends on it ever since. It's gone up, it's gone down, it's gone up, it's gone down. That doesn't matter. We're still taking the dividends and using them. Dad bought Coca-Cola stock because he worked for Coca-Cola. Coca-Cola stock's been up, it's been down. When he died, he had $750,000 in Coca-Cola stock. What good did that do him? Absolutely none. So, so that's it. So in your 401ks, you're basically buying. There's somebody out there watching after you to make sure you don't have some rotten apples in the core. Well, that's one of the other strategies. 59. Number 59. The unemployment rate in the state of Arizona, 4.1%. Assume that 100 employable people in Arizona are selected at random. So I got 100 people at random. A, what is the expected number of people unemployed? Okay, so the expected number of people unemployed would be the number times the probability. 100 times 4.1%. 4.1 people? Yeah, 4.1 people. This is where I can't have a point person, right? So I'd probably say 4. B. What are the variance and standard deviation of the number of people who are unemployed? Okay, so the variance is going to equal N P 1 minus P. 100.041.0 959. .9319, square root of that number. Standard deviation 1.98. And it would seem to me like I should be able to make my sigma just a little bit better than that. How's that? Is that better? Okay. Number 65 is next. A deck of playing cards contains 52 cards. Is that true?
Yeah.
No, there's 2 jokers, so there's 54. And then there's probably a blank one, so there's probably 55, right?
56 count the rules.
56 is probably a rule card. These guys are hosing us over here. All right. 4 of which are aces. Okay, well, we can agree that there are 4 aces in a deck of playing cards. Okay, we may not be able to agree on 52 being in the deck, but I think we can agree on 4 aces. What is the probability that the deal of 5-card hand provides for a pair of aces? Okay, so N is 52. Little n is 5. I'm dealing out 5 cards. Little r is 4 because there's 4 aces in the deck. And so we want 2 of them to be aces. So this is the hypergeometric probability. So we're going to take 4 things, 2 at a time. My 4 aces, I need 2 of them. I have 48 things left over that are being taken 3 at a time that I really don't care about. And then I got 52 things, and I'm dealing out 5 of them. Okay, so we use our calculator. 4 things taken 2 at a time times 48 things taken 3 at a time divided by 52 things taken 5 at a time. 0.03993 is the probability of getting 2 aces, and that's why if you have 2 aces, you're in a 5-card game, you go and bet everything because no one's going to beat you, right? Most of the time, 2 aces will win. Oh, what do we do? Yeah, that's the A part. B part. Exactly 1 ace. Okay, so that's the A answer. B answer. Exactly 1 ace. So I'm going to take 4 things, and I only want 1 of them.
You couldn't just take that number and divide it by 2.
No,
The other one's 2, so you can't just put that now.
no. No, it's not that simple.
Of course not.
No. Exactly 1 ace. See, if I divide that number in 2, I'd have 0.01 something, right? 0.01 whatever, 19. So your view is that I should be able to divide this in
Which
half,
makes
right?
sense to me.
But think of it this way. I'm dealing the cards. If I'm gonna, let's say I have two stacks here. This guy has two aces, that guy has two aces, none and one. That guy has one ace, that guy has one ace, that guy has one ace, that guy has one ace. There's a better probability that I'm gonna get an ace than there is.
For two rather than.
That's right. So the chances of me having a ace is gonna be higher than me having two aces,
Oh,
right? Yeah, so that's why I can't divide that answer by 2. That wouldn't make any sense. All right, so I got 4 things taken one at a time, 48 things left over taken 4 at a time, and I got 52 things taken 5 at a time. So that's the math I want to do. Okay, so 4 things taken one at a time times 48 things taken 4 at a time divided by 52 things taken 5 at a time, and I end up with 0.2995. So greater than a quarter of the time if I deal out, can I deal out 10 cards, 10 hands? Yeah. Anyway, so if I deal out 4 things of 5, the chances are pretty high that one of them's going to have an ace. Anyway, C. No aces. No aces. So 4 things taken 0 at a time, 48 things taken 5 at a time, divided by 52 things taken 5 at a time. Now the chances of having no aces should be, well, it can't be 1 minus that number because this isn't the probability of 2 or 3 aces or 4 aces. Anyway, so 4 things taken 0 at a time is going to be 0. So I got 48 things, or it's going to be 1, taken 4 at a time divided by 52 things. I'll blew it already. 48 things taken 5 at a time divided. I'm talking and not punching the keys, that's my problem. Divided by 52 things taken 5 at a time. 0.0749. Is that what you got? So the chances of having no aces is better than the chances of having 2, but the chances of having 1 is pretty high. And why is it that my answer is wrong? What fat fingered key did I hit?
I was gonna say that's not being fair.
What did you get?
I got 0.6588.
That's what I got too.
0.6588. I believe that. That's a much better answer. And delta, we want at least 1 ace. At least 1 ace. Okay, so at least 1 ace would be 1 minus no aces, right? So this is the no ace guy, so at least 1. 1 minus 0.6588, giving us, that's a 2, that's a 1, that's a 4, that's a 3. So I wouldn't go back and calculate 1 ace, 2 ace, 3 ace, 4 ace and add it together. I'd just say I know what it is with no ace and subtract it from 1. All right. With that, we are done with chapter 5, And we are ready to proceed to chapter 6.
Should we do the test together?
I don't understand together.
As
You
a
want me to
group?
you want me to take the grade on it and divide by 9? Is that what you want?
No, let's do it as a group.
No.
Just one.
Well, I'm going to make up 5 different ones anyway, 6 different ones. Yeah. 9 different ones? Yeah, that's what I remember. All right. So, what is the, okay, there's number 6. So, what is the probability of Emily calling me up, telling me she's going to be 10 minutes late?
Very high.
Yes, that's exactly what happened. Yes, I did get that phone call. Okay, maybe we're in, chapter 6, continuous probability distributions. Okay, so the last time we were discrete probability distributions. So that meant that I could have a deck of cards with 52 in it, but I couldn't have a half ace, right? Now I can have continuous ones, uniform probability, normal probability, normal approximate binomial probabilities, exponential things. So here's a uniform probability, then there's a normal probability, an exponential probability, and are we going to see the last one or not? This reminds me of my fuzzy math class. The continuous probability. A continuous random function can assume any value in an interval on the real number line or in any collection of intervals. Okay, it is not possible to talk about the probability of the random variable assuming a particular value because it is continuous. Instead, we talk about the probability of the variable assuming a value within some interval. So let's take the color red. Is red a discrete thing? Or if we came to class next on Thursday, all wearing a red shirt or a red blouse, we would have different colors of red, wouldn't we? Yeah. So that would be a random variable that's not. Red would not be discrete. Blue would not be discrete. It's a range of things. The probability of a random variable assuming a value within some interval x1 to x2 is defined as the area under the graph. Now, area under the graph is also an integral, so that's integration in calculus. So maybe we'll see a calculus thing here. I doubt it, but we might. It's possible. So I've got some probability that I'm going to be between x1 and x2. Uniform probability could be uniformly distributed whenever the probability is proportional to the length. It could be a density function. So here we have some density function. A is the smallest value, B is the largest, and I go between those two. I have an expected value. If I have uniform probability, which is a rectangular thing, I take the biggest one, the littlest one, I divide by 2. I have a variance. Why am I dividing by 12? I guess I am. Statter's buffet. Oh, buffet. Customers are charged for the amount of salad they take. Sampling suggests that the amount of salad is uniformly distributed between 5 and 15 ounces. Okay. Uniform probability distribution function. Somewhere between 5 and 15, so the probability is 1/10. Expected value, 10. Variance, 8.33. based
So the
on,
variance you subtract the two.
yeah, the two ends of the probability. And I'm dividing by 12. Now, who picked up 12? There's a time in our history, no television, no radio, no cell phone. Nobody remembers that time, right? But that did occur. And we still did math. And we still did science. And we still read books. It was really a wonderful time. Now we can barely, we don't know what a book looks like unless we have a Kindle and it's on there, right? So during that time, people would sit around with their pencil and their paper doing things. And that's why we know we divide by 12. If we went back and asked ourselves, how do we know we divide by 12 today? We wouldn't know. It's lost in antiquity. Okay? There might be 10 people in the world that care and they know. But the rest of us, we just say, okay, going to take the variance, divide by 12. Okay, fine. All my solids, I have a 1/10 of a probability function that I'm going to be anywhere in that interval. What is the probability that a customer will take 12 to 15 ounces? That would be 0.3. So 1/10 times my range of 3. Area is a member of probability. Area under the curve. Probability, blah, blah, blah. Normal distribution. Right? All right, okay, we agree with that. Test scores, people do it. Mathematicians. Some French guy gave this normal curve to us in 1733, before there were televisions, before there were stereos. And he decided it was normal. There is the normal distribution probability function. So I need the standard deviation, I need the mean, I'm using E, which is the base of the natural logs, and I'm using pi. Where's pi? There's pi, square root of 2 pi. Again, the monks in Europe sat there doing their math over and over again, getting the same numbers over again, looking for a relationship. They found this relationship. Now we get to play with it. E to the minus something, and that's going to be a minus number as time goes on. This E thing gets smaller and smaller because it's a negative exponent. Characteristics. The distribution is symmetric. Yeah. With screwedness of 0. Okay, so if I go down the middle, I have half on one side, half on the other side. All right. The mean mu is the standard, and its standard deviation. Okay, there's the mean mu. Oh, do I have to go back? May have gone too quick. All right, and we have some standard deviation sigma. All right, excellent. I'm sure we do. We have a mean, we have a median, and we have a mode in the curve. And the highest point in the curve is where all three of those guys exist. So the most data points is there, the mean is there, the median's there. Okay, that's fine. The mean could be some negative value. Oh, there we go. Now I have a negative value for the mean. Isn't that lovely? And I probably have a 0 value. There I have a 0 value. And then I have a positive value. Standard deviation determines the width of the curve. whether it's flat or it's peaked. So the bigger the standard deviation, the more spread out it is, the smaller it is, the closer it is to the mean. And the probabilities are given as the areas under the curve. So we have 0.5 on that side and 0.5 on that side. Isn't that lovely? So no, we won't. We won't confuse the issue at all. We'll just move on. Then we have some rules. The first rule says 68.26% of the values are going to be plus or minus 1 standard deviation from the mean. 95.44% are going to be plus or minus 2 standard deviations from the mean. 9.99%, 72%, going to be 3 standard deviations from the mean. We'll try to move back again. Okay, so those are our rules. 68 point something percent plus or minus 1 standard deviation of the mean, 95% plus or minus 2 standard deviation, 99.72% plus or minus 3 standard deviation. So us in the room, the 10 of us, are there 10 of us here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Who's missing? No, we're all here. How many of us are within 3, outside of the 3 standard deviations of the mean in everything we do in our life? Okay, all you raise your hand. Of course we are. That's why we're here, right? Now, if we did what everybody else did, would we be here? No, we wouldn't be. Okay. So think of it that way. You're the top 0.3%. Something like that. Maybe. Does that make any sense? So then we're going to apply these rules. All right, so on plus or minus 1 standard deviation, oh, we're just going to draw pictures. Okay, we're going to draw pictures and say the same thing over again. Okay. Can I interpolate between those numbers? No, it's not a straight line, right? So I'm sort of stuck with those characteristics. Standard normal probability. A random variable having a normal distribution mean of 0 and a standard deviation of 1 is a standard normal probability. So saying that you're a 0 isn't an insult anymore, because that's just standard normal probability. At 0, that's where everybody should be, about there. Yeah. And then we have a z is going to be used to designate the standard normal random variable. Okay, so we're going to take our data and assign it z numbers and put it on the z curve, where our standard deviation is 1, and I have a normal standard deviation. Converting standard normal deviations, so my z number, x minus mu, divided by the standard deviation, will now give us the z number. Now, I look at that equation and I see 4 variables. I could give you any 3 of them and you'd have to calculate the other one. See how that works? So that would be a reasonable thing to do. And of course, if we're going to want to make a curve that's a standard normal deviation curve, we're going to have 5, 6, 7, 8 or so z's anyway, in order to have it look right. So z is the measure of the number of the standard deviations of x's from mu's. Well, that didn't make any sense to me, but that formula is something we'll use sometime. The PEP zone, they have to be making this up. Oh, this is a place that sells cars. Sells auto parts and supplies, including popular multi-grade oil when in stock. And and drums up to 20 gallons. Okay. Let's determine the demand for replenishment diminishes over time with a mean of 15 gallons, a standard deviation of 6 gallons. The manager would like to know the probability of stock out during replenishment lead time. In other words, what is the probability that the demand will exceed 20? That's what he wants to know. All right, so solving for the problem, we're going to convert x to a standard deviation. Okay, I know x, I know my mean, I know my normal thing, so my z is going to be 0.38. Find the area under the curve of the normal z. Alright, so here we have a chart that tells us the area under the curve, which means I won't have to do the calculus to solve the area under the curve. So I want a z of 0.83, so I look that up, and now that gives me that probability. And if I look in the back of my book, I probably have that table sitting in the appendixes before the answers, and
Like 629.
629. I'll get there, I imagine. No, not 629. There it is, on page 605. We have our z numbers for the areas under the curve. Okay, so much for having to do calculus. Bummer. Solving the probability. Compute the area under the standard deviation curve, 0.3. So z is going to be greater than that. 1 minus the area, blah, blah, blah. The probability of needing more, so 20%. 20% of the time I'm going to run out. Alright, that's probably not good. So that's showing where my 0.83 is. The area of the curve up to 0.83. All the stuff back there. 1 minus that number gives us probability of running out. Standard normal probability distributions. Okay. I want to have no more than, that was 20% of the time. I want it to be no more than 5% of the time running out. That's my job. So now I got to find the z corresponding to that situation. Where's my reorder point? So I figure out where is my 0.05, what my z is for 0.95. So I go back to my chart and get it. And okay, there I'm back in my chart. And 0.95 is someplace between there. So we'll call it 1.645. Halfway in between. So we found it. Now we got to put it in a normal value. So we use the formula again that we had before, and we come up with x is 25 gallons. So if I reorder 25 gallons every time, I'll only run out 5% of the time. That's what that's trying to tell me. Solving for the reorder point. By raising the order from from 25 to from 20 gallons to 25 gallons, out of stock decreases from 20% of the time to only 5% of the time, and everybody is more happy. Normal approximation of binomial probabilities. When the number of trials n becomes very large, evaluation of the binomial probability function is hard to calculate. Okay, so that's that a plus b raised to some number. So as I get more and more trials, that number gets very large and it gets out of hand trying to calculate. The normal probability distribution provides an easy-to-use way to approximate the binomial probabilities, where number times the probability is greater than 5, and number times 1 minus the probability is greater than 5. So as long as I've got large numbers, this is going to work. The definition of the normal curve is set at mu equals np and my standard deviation as you see it. All right. Add and subtract a continuity correction factor because a continuous distribution is being used to approximate a discrete distribution. Okay, well that's good. For example, we have x is equal to 12, and the continuous thing is going to be 11.5 or whatever. Okay, well, that's fine. Suppose a company has a history of making errors on 10% of its invoices. So I got 100 invoices, and 12, we want to calculate what's the probability of 12 of them having errors. Okay, so we find that the mu is 10, the standard deviation is 3, and we want to find out the probability that 12 have errors. The normal approximation to the binomial probability, n is 100, p is 0.1. All right, so we want that hunk of things between 1.1, 11.5, and 12.5. So we're going to convert these to z numbers and go get it off our z graph. That's what we're probably going to do. We will see. No, we're not. We're going to go and look at 12 using the binomial probability, and then we're going to go look at 11.5, and we're going to subtract those two. So the probability of 12 invoices being messed up out of 100 is 0.1052. Just what I needed to know. Exponential probability distribution. So now we have something that's not very pretty. So I've got some density function. Expected value or mean. As x gets bigger, this number gets smaller, the whole thing gets smaller. The time between arrivals of cars that fill up at the gas station, 3 minutes. What's the probability that it'll be less than 2? Okay. So the probability of more time going away is going to be whatever it is. So I end up finding the area under that curve by using my equation. And then, oh, I guess I'm done. The Poisson distribution provides an approximate distribution, a number of occurrences per interval. The exponential distribution provides approximate distribution, length of the interval between occurrences. All right, whatever. End of chapter 6. Excellent. All right. Now it's time to work some problems. And we'll start with number 5. During the driving distance of the top 100 golfers on the GPA tour is between 284.7 and 310.6 yards. Assume that the driving distance for these golfers is uniformly distributed over the interval. Okay, so I have some chart of this. I've got some uniform distribution between 284.6 and 310.6. Okay, so that's what I've got. All right. Give a mathematical expression of the probability density function for the driving distance. Okay, so I'm going to look at this interval 310.6, 284.6, and I'm going to come up with something. So my interval is
Should it be 284.7?
yeah. Who put the 6 there? Oh, that was me. So I got a 25.9. So my interval is 29.9. So my probability function is 1 over 25.9 for 284.7 less than or equal to x, less than or equal to 310.6, and it's going to be 0 for everything else. All right, so that's my A answer. My B answer, I wasn't very professional. B answer. What is the probability that the driving distance of one of these golfers is less than 290 yards? So the probability less than 290 yards for one of them. Okay, so that's going to be 1 over 25.9 times the range 290 minus 248.7. Two nine zero minus 284.7 equals times, divide by 0.25.9. Boom. 0.2046 or thereabouts. So that one of 100 guys is going to be down that way. Okay, that's probably going to be me. See, no, I don't golf. See, what is the probability that the driving distance for one of these golfers is at least 300? So probability at least 300. 1 over 25.9 times at least. That means it's got to be more than 300. So 310.6 minus 300. Um, 0.4092. Delta. What is the probability that the driving distance for one of these golfers is between, so probability to be between 290 and 305. 1 over 25.9, 305 minus 290, also known as 15. .5790. E. How many of these golfers drive a ball at least 290? Probability that X is greater than or equal to 290. 1 over 25.9. What's the top guy again? 310.6 minus 290. .7952. So much for problem number 2 or 5. What problem are we on anyway? 5. 5. Move up, move down, move all around. Okay, relatively happy. Number 11. Given that Z is a standard random variable, compute the probabilities. All right, so we want to get the probability that Z is less than or greater than 1.0. The probability that Z is greater than or equal to -1. The probability that Z is greater than or equal to 1.5. The probability that Z is at -2.5 is less than or equal to Z, and the probability that -3 is less than Z is less than or equal to 0. Okay. Well. Okay. I got the standard deviation thingy, right? and I've got 68% one standard deviation, 95% two standard deviations, and 99% three standard deviations, right? So if I want greater than, if z is less than or equal to 1, that would put me right here because the standard deviation is at 1. So I want that part. That's that way. So what would that be? That would be, So that would be,
understand you got like 68 and 95.
Yeah.
oh, I remembered that from earlier. Don't remember that from earlier?
Numerical rule.
Yeah, page 241. So we'll use the graph on 241. Yeah, we don't have to. Well, we're gonna do it anyway. So when I use the graph on 241, there's 0. There's 1 standard deviation, 2 standard deviations, 3 standard deviations. So on the outside of 3 standard deviations, I would have 0.0035%, 0.0035%. That's outside because I have 99.7 between there and there. So half of what's left over has to be in those spots. And when I look at 2 standard deviations, okay, so I have 2 standard deviations. I have 95.4, which means I have 4.6. Half of 4.6 is 2.3%. So I have 2.3% that way. I have 2.3% this way. And then I'm going to look at 1 standard deviation. At 1 standard deviation, I have 68.3. 100 minus 68.3 divided by 2, 15.8. So I have 15.8 that way and 15.8 this way. Okay, so that's what I'm looking at. So I have inside here, I can come up with the 68.3, 68.3, and for 2 standard deviations, I can come up with 95.4, and with 3 standard deviations, I can come up with the 99.7%. Okay, so on the inside, but now I'm looking at what's on the outside. So if z is greater than or equal to -1, which puts us there, then this is going to have to be that 15.8, 0.158. If z is greater than -1, then it's everything that way, so it'd be 1 minus 0.158. 1 minus 0.1558.
Oh,
0.842. If z is going to be, now I can't do this one because that's a half a standard deviation. My chart won't work. That's a half standard deviation. My chart won't work. But if I want -3 to 0, okay, so 0 all the way that way is going to be a half. So I'm going to subtract the portion that's the -3 guy. So that's going to be 0.5 minus .0035. .4965. Right, so now I've got to do the ones that are, so I did those from knowing what my standard deviation curve looks like. Now I've got to do the ones that are not that way. Okay, so I go to the back of the book, and we decided that was on page 600 and something, right? 605. Okay. So we want less than minus 2.5 is less than or equal to z. So we'll do that one first, and we look in for minus 2.5, and we read a number of 0.0062. Then we want to know greater than 1.5, minus 1.5. So we go 1 minus, we look up the minus 1.5 guy, 0.0668. 1 minus 0.0668. And we get a 0.9332. Okay. Then we're going to go back and redo the ones that we just got it off our chart, and we said z was less than or equal to minus 1. So I look at minus 1, and I get 0.1587. Do I have 1.5? Yes, I do. And then I want to have z greater than 0.1. Well, that'd just be 1 minus that number. That'd be okay. We did those guys. We want z to be between minus 3 and 0, so we'd have to look up the minus 3 guy. We have him, and we do the same thing. Okay, so the first time through, we did an approximation thing based on what our curves look like. Second time through, we did it again looking at the z table in the back of the book. Which would you like better? Not thinking and using the back of the book. Okay. I will accept that answer.
Can we use the book on the test?
I would hope so, yeah. I mean,
It's gonna be take home anyway.
if you're going to have it at home and you left your book in your car,
You have to leave your books in
And-
today. He's gonna take them all.
so that what's the probability of you're doing the test at home and
I don't know.
and you're not using the internet to Google any of the things, and you're
I don't even know how to do
and
that.
you're not, and your book is in the car, and your girlfriend just took off with your car taking your book to Des Moines. All right, so we covered all that probability. Number 17. For borrowers with good credit.
For what?
Borrowers, number 17.
Well, yeah.
So we're going to borrow with good credit. Installment accounts that, standard deviation that. So my mean for my borrowing, 15,100, that. And the standard deviation around that mean is 3540. I should go shoot myself. I'm so far away from that. That's a different issue. What is the probability that the debt for a borrower with good credit is more than 1,800? 18,000. Okay. So we know mu, we know the standard deviation, we know z. Z is the amount minus the standard deviation divided by sigma. So 18,000 minus 15,015 divided by 3540, and now I've got a Z number. 18000 minus 15015 divided by 3540 equals 0.843. Alright, so I know it's 48.3. So now I want the probability that x is going to be greater than 18,000 is going to be 1 minus the probability that z is less than or equal to 0.843. Okay, so now I lost my place in the book, but I can find it quickly, I imagine. So I go back to page 605, and I look at 0.84, and that's the best I can get. So I'm going to use 0.84. So I'm going to go 1 minus 0.7995. 1 minus 0.7995. 0.2005. So that's going to be my A answer. I'm doing 17. Okay. I'm going to look at my B answer. What is the probability that the debt is going to be less than 10,000? Okay, so my B answer, I want to find a Z value again. So 10,000 minus 15,015 divided by, why can't I remember these things? 3540. Okay, 10,000 minus 15015 divided by 3440 minus 1.42. Okay, so the probability for Z being less than or equal to 1.42 minus 9. Okay, go back to the back of the book again. 1.42 0.0778. .0778. Charlie, what is the probability that the debt is between, okay, so we want between 12,000 and 18,000. Okay, so we already know the probability of greater than 18,000, right? So the probability of x being greater than 18,000 from A above was 0.2005. So now we need the Z value for 12,000. Z value of 12,000. So that'd be 12,000 minus 15,015 divided by 3450. Did I get it right that time?
541.
It's 3,540. Another learning disability problem there. 130. No. Minus 0.851. Okay, so the probability that Z is less than 12,000 is minus 0.85, and I don't need a 1, 0.1977. 0.1977. Do I subtract those two? No, I don't. So I think I'm going to take a break. Control Shift.
Can we just add those two together?
Okay, so we want the probability that minus 0.85 is less than Z is less than 0.84. That's what we want. Okay. So the probability that that 0.2005 guy from A, so to be less than that, I'm going to be 1 minus 0.2005, and to be greater than this guy, I'm going to be a minus 1.977. So the whole is 1. The top part greater than that guy is here. Less than that guy is there. And that's going to be my final answer. 1 minus 0.2005. No, it isn't. Calculator's not on. 1 minus 0.2005 minus 0.1977. 0.6018. And so that's the probability of being between $12,000 and $18,000 in debt. What is the probability that the debt of the borrower with good credit is no more than 14,000? Okay, no more than 14,000 delta. Okay, so we needed Z value for 14,000 minus 15,015 divided by 3,540. So we find that Z number. Minus 0.287. Minus 0.287. Okay, we look in the back of the book. The probability that minus 0.287 is less than Z, 0.287, we'll round it up to 29, .3859. 0.3859. Okay, enough with that one. Moving on. And number 23 is next. Oh, I'm sorry. Moving back.
Oh, I got it.
You got it? Lots of numbers written down there. But I like this.
So that .3859, that's gonna be a shaded area.
Yes. Exactly.
And then,
It wants to know the probability that the debt is no more than that. So that's exactly right. So I've got some normal curve. There's my minus 0.287, and I want that shaded area, which is exactly what the chart gives me. All right, looking at 23. The one, the time needed to complete a final exam in a particular college course normally is a mean of that. Okay. Number 23. My mean is 80 minutes. And standard deviation, 10 minutes. Answer the following. What is the probability of completing the exam in less than an hour? Okay, so we need X. We need a Z. So Z is going to be 60 minus 80 divided by 10, also known as minus 0.2.
60 minutes.
Is that what that is? Minus 0.2? Yeah, minus 0.2. Okay, we go to our chart and see the probability of minus 0.2 less than or equal to Z is 0.4207. If I could do the math right. Someone was telling me I was wrong, right? So it's minus 2, not 0.2. It's 20 divided by 10. All right, so minus 2. 0.0228. Okay. B. What is the probability that a student will complete the exam in more than 60? So we want 60 to 75 minutes. Okay, so the probability, we need a Z number. So I need a Z number for, did I just do 60? I just did 60. So I already have the Z number for 60, which is going to be minus 2. I need a Z number for 75. So I got 75 minus 80 divided by 10. 0.5. Okay, so the probability that minus 2 is less than Z is less than minus 0.5 is going to be whatever the minus 0.5 guy is, 0.3085 minus the minus 2 guy, 0.0228. Point 2857. C. Assume that the class has 60 students that take the exam in a 90-minute period. How many students do you expect will be able to complete the exam in the allotted time? Okay, so we need the Z value for 90 minutes, which is going to be 90 minus the mean, which is 80, divided by 10, which is 1. Right, so the probability of 90 being less than or equal to Z, 1 being less than or equal to Z. Is 0.8413. 0.8413. There are how many students? There are 60 students. So 60 times 0.8413 50 students. We expect 50 students to complete.
We're looking for unable.
Unable?
Yeah.
How many students do you expect to be unable? Okay, so I would go 60 minus 50, call the correct answer 10. And then I'd erase this circle around this guy, indicating that he was correct. Okay? Number 29. An Internal Revenue Oversight Board surveyed found 82% of taxpayers said it was very important for the IRS to ensure that high-income taxpayers do not cheat. Do we care? All taxpayers. Do you guys cheat on your taxes? Don't answer that. Go ahead. How many cheat on their taxes? Raise your hand. No? Okay. You're not going to raise your hand. Okay. That's fine. Don't have to. For a sample of 8 taxpayers, what is the probability that at least 6 say that it's very important that somebody else not cheat? Well, isn't that good? A. So this is 29. 29. Okay, so we want the probability of some function, because we're using the binomial thing, nx, probability x, p minus probability, n minus x. So that's what we're doing. We have 8. The probability for a sample of 8 taxpayers, what is the probability that at least 6 say it's very important? 0.82 raised to the 6th power times 0.18 raised to the squared power. Okay, so that's what our equation is saying there. So 8 items, taken 6 at a time, times 0.82 raised to the 6th power, times 0.18 squared. 0.2757. Okay. Lucky guess, I know. For a sample of 80 taxpayers, what is the probability that at least 60 say it's very important that somebody else doesn't cheat? Okay, so B. We have 80, 60, 0.82 raised to the 60, 0.18 raised to the 20. 80, 60 times 0.82 raised to the 60th times 0.18 raised to the 20th. 0.0303. Hmm. This is B. Yeah, it must be right. Okay, next one. As the number of trials in a binomial distribution gets very large, what is the advantage of using normal approximations? And the advantage is time to do the calculation, because if I have to do that, this guy took longer in my calculator than the first guy. In D, when the number of trials becomes large, would developers of software prefer to use that, the binomial distribution, or normal binomial? To use a binomial distribution, they would rather use the binomial distribution because it's less calculations. All right. Next problem. I don't know what the next problem is. Anybody know what the next problem is?
35.
35? Okay. 35. It looks like we're using MATLAB to do it. 35. The time between arrivals of vehicles at a particular intersection follows a binomial probability distribution with a mean of 12 seconds. Okay. So my mean is 12 seconds. Sketch this exponential probability. All right, so where is okay, so we want f of x is equal to mu to the x e to the minus mu divided by x factorial. Okay, so that's what we're looking for. Okay, so we'll go with f of 1 because that's easy to do. So f of 1 would be 20 raised to the first power e to the minus 20 divided by 1. Yeah. All right.
Okay, where does that 20 come in?
Right here, 20
Both sides.
seconds. Oh. 20 is the mean. Right there. So 20 is the mean. 1 is the x. There's my 1. There's my 1 factorial. E to the minus 20. 20 times exponential raised to the minus 20. That is really small. So what am I doing wrong? Mu raised to the x.
Isn't the mean 12, not 20?
$35. The mean is 12. How did I get 20? Oh, okay.
Do we have the E in our calculator?
Yes, you do.
Yes. Yes.
12 e to the minus 12. That's still going to be awful small. I'm still getting something too small, 0.00007. And that
That's it?
exponential probability. Okay. No, that's not it because it's wrong. Bigger eraser. That's better. So f of x is 1 over mu e to the minus x over mu. That's the function we want. Okay, so f of 1, well, f of 0. F of 0 is going to be 1 over 12. That's better. .083. Okay, much better. And then we'll go f of 6. 1 over 12 e to the minus 1/2. .05. And then we'll go f of 12. 1 over 12 e to the minus 1. 0.03. And do we have enough data points yet? We'll use f of 24. 1 over 12 e to the minus 2. Point 0.01. So now we'll draw a table. 6, 12, 24, 0.03, 0.08, 0.08, 0.05, 0.03, 0.01. There. Okay. Part A is done. Part B. This is 35. What is the probability that the arrival time of the vehicle is 12 seconds or less? So we're looking at the area under the curve right there is what we're looking at. So the probability number is to be probability time is less than or equal to 12. Okay. 1 minus e to the minus 12 over 12. 1 minus e to the minus 1. 0.63. C. What is the probability that the vehicle is there in 6 seconds or less? Probability t less than or equal to 6. 1 minus e to the minus 6 over 12. Point 39. D. What is the probability of 30 or more seconds between arrivals? Okay, so we want the probability t is greater than or equal to 30. Okay, so it'd be 1 minus the probability t is less than 30. 1 minus e, 1 minus 1 minus e to the minus 30 over 12. Alright, so that's what I'm doing. 1 minus, parentheses, 1 minus e to the minus 30 divided by 12, close parentheses, 0.082. Okay? Now, looks like I have 1, 2, 3 more problems to go. Well, we still have a quiz to do. So what I'm thinking is, on Thursday, I do those 3 problems. I hand out the test. I hand out the test. You guys start working on the test. Prior to 7 o'clock, you have turned your test in. I have graded it and handed it back to you for a second opinion that you do someplace else. And you bring the test back on Monday. Do you think that'll work?
Yep.
The other option is that we go longer. But, okay, so I'll pass out the quiz.
Oh, yeah, yeah. That's the same issue.
I don't wanna go, but I have to.
Oh, I got a better idea. Why don't I, between now and Thursday, do the last three problems and put them on the web?